I'm John Pickle, and I would like to explore some ideas about using digital cameras to study science. One of the benefits of having a movie on your computer is you can change the speed and direction of how you view it. When the movie is viewed in ways we aren't used to seeing, it's easier to notice patterns we often take for granted. If you are watching this movie for the first time, consider turning off the sound now so that you can see what you observe on your own with the movie clips that follow. In this time-lapse movie of sunrise over the Atlantic Ocean, notice that the sun doesn't rise perpendicular to the horizon. Rather, it rises at an angle. The angle from vertical is the latitude of your location. In this movie, I was at the Cape Cod National Seashore, or roughly 41.8 degrees north. At the equator, where the latitude is 0 degrees, then the sun rises perpendicular to the horizon. At one of the poles, where the latitude is 90 degrees, the sun moves parallel to the horizon throughout the day. And if you're in the southern hemisphere, the sun rises from right to left, which is opposite from what we see in this movie clip. You may also use this movie to study the wave patterns, the timing of the waves, the differences in the wave heights, the timing of the tides, and the sandbar patterns as the tides retreat. Another way to study how the sun moves across the sky is by watching how the shadows move. In this movie, near local noon, the shadows move about 12.5 degrees per hour, and yet towards sunset they move about 7.5 degrees per hour. So consider, if you were at the equator during the equinox, the shadows would not change angle after local noon. They would only get longer. Do all the clouds in the sky move in the same direction? In this time-lapse movie, the camera is pointed northeastward and tilted 45 degrees upward, so the bottom of the camera points toward the northeast and the top of the camera to the southwest. The upper-level clouds, the cirrus, the cirrocumulus, and the cirrostratus, are moving to the west-northwest, so the winds at that level are blowing from the east-southeast. The lower-level cumulus clouds are moving to the south-southeast, so the lower-level winds are blowing from the north-northeast. In this example, the clockwise change of cloud motion with height is a result of warm air being blown into the region. If the cloud motion changed counterclockwise with height, then cold air is being blown into the region. Do clouds change direction in the sky? In this example, they do. The low-level stratocumulus clouds are originally moving to the west, so the winds are from the east. Over a period of 10 to 15 minutes, the clouds changed direction and began moving toward the south, so the winds shifted counterclockwise during this time. Take a closer look at this movie. Notice that the holes in the clouds are rotating clockwise. This indicates that there's a circular column of sinking air that is rotating. This is a very unusual cloud feature and one that needs to be examined in more detail. Do we see different patterns when the time between frames of a time-lapse movie is shorter or longer? In these 4 examples, as the time length gets shorter between frames, you can see the rolling convection cells in the severe weather as it approached Concord Academy several summers ago. At the end of the clip, the shelf cloud appears just above tree line, and this is when I took the camera down. It began hailing 5 minutes later. In all 4 movies, you can see the direction of motion of the clouds, but you don't see the strong convection pattern in the cloud motion with the longer time intervals. You really need the shorter time scales to see this. Because the digital camera measures red, green, and blue intensity simultaneously, we can analyze if all the colors are equally polarized. In this example of the light reflecting off the leaves of a plant, the blue light appears to change intensity more than the other colors as the polarizing filter is rotated. Consider that butterflies detect polarized blue light to identify what leaves they eat. Digital movies are great tools for analyzing the motion of objects. Study the effects of gravity, air resistance, friction, and collisions in 1 and 2 dimensions. Objects moving in circles may also be studied. Study the motion frame by frame to measure the position, velocity, and acceleration of the moving object. Set up crystal growth experiments and study how quickly the crystals grow. Is it constant or are there periods of rapid growth? By changing the conditions, you may measure the growth rates and size of the crystals. These experiments are useful for both chemistry but also in geology, where the growth of crystals is essential in understanding how molten rocks solidify and how evaporites form in shallow salty seas. You can also study how plants grow, and in some cases, how plants die. Measure the rates of growth of the stem's height and thickness, the height and area of the leaves, when flowers and seeds appear, and how the plant moves over time. Notice that the established leaves don't change height with time. This is similar to limbs of a tree. If you hit your head on a tree in the neighborhood, remember it will be at that same height the next time you walk by. The bottom line is you can study just about anything of interest with a digital movie, anything that moves, changes shape, or color. So consider, measure your golf swing, your dance steps, your soccer kick, how you ride a bike, how far you can jump on your bike. Whatever you want, consider filming it and then studying it.